This is for the Chemical Engineering Thermodynamics 1 course. In this video, we will be presenting about our integrated project, where we got the topic gas-fired power plant. We are from Group 2 and here are our group members. For the introduction, in order to create a gas-fired power plant, a few criteria are needed. One of it is it has to be able to burn natural gas, which is mainly methane, to generate electricity. In order to generate enough electricity, which is 32 megawatts, the use of proton TRL for gas turbine is required. In this project, we will be able to determine the efficiency and the total backward ratio to run the power plant. Besides that, we can also determine the amount of natural gas required, air-fuel ratio, and also the actual power produced. Next, we will also be able to calculate the number of equipment and also figure out the type of cycle and also the schematic diagram.
As we can see from the slide, the diagram shows a schematic diagram of gas-fired power plant. In the first cycle of gas turbine, the low pressure air is compressed to a high pressure gas after going through the compressor. The high pressure of air then combined with fuel that injected to the combustion chamber form a high pressure and velocity of the gas. The gas from the combustor then enter the gas turbine. Gas turbine then expand the atmospheric pressure from the inlet of the turbine to generate electricity, also transfer the exhaust gas from the turbine to the heat recovery steam generator to be used again. The process is then continued in the next power cycle, which is the steam power cycle. The products of the heat recovery steam generator from the previously cycle will resulting in steam, which is a superheated vapor. When the steam enters the steam turbine, it will expand and produces work by rotating the shaft connected to an electric generator. The steam, which is in saturated liquid vapor mixture, will experience a temperature and pressure drop after entering the gas turbine. The steam from gas turbine will enter the condenser to condense the steam to a saturated liquid form. The liquid form of steam then enters the pump and the temperature will be increased due to decrease in specific volume of water. Concerning of greenhouse gas emissions, carbon capture storage facilities is installed, which is the flue gas from the power station is passed through the base solution of Monash, which is monoethanol amine, also known as MEA. The liquids then absorb CO2 from gas mixture and the nitrogen gas is separated after reacted with MEA. The rich solution of CO2 is then being heated, which results it will be released. The nitrogen gas from the results will be released that in a clean and safe environmentally. Meanwhile, CO2 gas stream can be used for the industry matters or stored deep underground sequestered, so it will not contribute to the global warming.
Icon simulations is used to ease the calculations. On the diagram shown is a gas power cycle simulations, and while creating these, there were few assumptions made that are shown on the slides. In the gas turbine power cycle, the working fluid is the air. The cycle starts with the low pressure air Q1 that is being compressed to a high pressure gas after going through the compressor. The high pressure of air S1 then combined with fuel that injected to the boiler with consumption of heat to combust, which produces carbon dioxide, water, and heat. As the working fluid is always considered as air, the air from boiler S2 is then entered to the gas turbine. Gas turbine then expand the atmospheric pressure from the inlet of the turbine to generate electricity through generator. This process produces transfer hot exhaust gas that then flows towards the heat recovery steam generator. Meanwhile, in the steam power cycle simulation, heat recovery steam generator, which has the same function as heat exchanger, then use the heat from the hot gases S5 to boil preheat water in the steam in superheated vapor S6. The steam then expands through a turbine generating electricity Q2. After the steam enters the turbine, the temperature and pressure of the steam is dropped, resulting in a saturated liquid vapor mixture S7. In order to enable the pump working completely, the liquid which is out of the turbine is then condensed using condensers S8. The process is then recycled through.
To calculate the efficiency, we plug in the Q out and Q in from the icon simulation values in the formula and we got 40.96% of efficiency. Total backward ratio is the ratio of total compressor and pump works to the turbine work. Total power ratio gives us the value of the turbine outputs that will be used again in the power plant. 14% of power ratio is considered as low already. For natural gas required, we need several assumptions before calculation by using the formula Qin divided by methane density and lower heating value. 99380.982 meter cube per hour of methane is required in combustion process. Air-fuel ratio is the ratio of mass of air to the mass of methane. From the theoretical combustion equation, 17.255 kg of air is needed to burn each kilogram of methane. Calculation shown, 2 steam turbines and 2 gas turbines will give the actual power produced, which is 768.8. We need 1 compressor, 1 pump, 2 steam turbines, 2 gas turbines, 1 condenser, 1 heat exchanger and 4 carbon capture facilities consist of 1 carbon capture storage, 1 compressor, 1 pipeline transport and 1 geosequestration to avoid greenhouse gas emission.
For the conclusion, the type of cycle used in the system is combined power cycle. Nowadays, these cycles are usually chosen for new gas-fired power station. Correct assumptions are important for calculations and designing the power plant. The power plant will be exposed to danger if the calculation and assumptions made are not accurate. The efficiency for power cycle is 41%, while the backwork ratio is 14%. About 99.4 km3 per hour of methane is required for combustion. Air-fuel ratio of the power plant is 17.3 kg air per kilogram methane. The actual power generated from the design power plant is 769 MW. That's all from us. Thank you.